So the first thing we're going to do is to focus today on writing constraints. Again, this new learning target 2.3 is on something called linear programming. It's a way to solve optimization problems. If you're trying to optimize the solution to a scenario where you can have multiple correct answers, how do we know which is the best correct answer to a problem to either like maximize or minimize our quantities that we're looking at, basically our X's and Y's. And so today's focus is going to be on writing these constraints. And a constraint is essentially what it looks like to you as an inequality. And the word constraint typically means something that restricts you. Like handcuffs are a type of constraint, right? Because it restricts your movement. So a constraint is an inequality. And we're going to, I know that's going to scare some of you, but you heard me say it earlier. We're going to have some word problems. Oh my gosh. Not word problems in math. Eeks. Yep, so we're going to be reading some word problems. And we need to determine what the unknowns are, because we're going to have an X variable and a Y variable. And we have to determine what are these unknown quantities. That's just where we start. You know, am I looking at apples and oranges? Am I looking at quarters or nickels? What are the two unknown things that we're going to be working with? And then you have to write these inequalities, and you have to use those types of words that refer to, well, a quantity or a number or a value. You know, there's 2 more than this, or 5 less than that, or at most 6. Those are all words that deal with an inequality. If I need to eat at least 2 pounds of French fries, then you could say X has to be greater than or equal to 2, because I have to have at least 2. I can have more than 2, but I can't have less than 2. And then we're going to be writing these constraints. They're really just inequalities. So we're creating several inequalities, like a system of inequalities.
Hello, Jack.
Yeah, what's up?
Are we supposed to be looking at something like notes, or because there's nothing on the?
Thank you so much,
Okay.
Carson, for
Yeah.
reminding me. That was awkward. Good call. Good call. Does that work better?
Yeah. Thank you.
Appreciate it. All right, so these constraints, and while cohort B is catching up, these are some of these word problems that I'm passing out to you that I had posted online. We're going to use these after the lesson, like to practice, so don't worry about them just yet, but we'll get to them. There you go. You're welcome. Now, writing these constraints, oh, I'm sorry, Parker. There you go, man. Writing these constraints, it's tough to teach someone how to do this. You really just have to look for it, because every word problem is going to be different. And so I'm going to show you what to look for, and just the more you practice these, the more you work through them, you're going to see what to look for. You're going to see how to create them. And so it's definitely the trickiest part. And so that's why I wanted to spend a day focusing primarily on these constraints, these inequalities, and setting them up. So we're going to take a look at one together, and then I've got just these practice problems for us to do kind of as a group to get familiar with it. And then once we have these inequalities, then we can graph them. And hey, have you graphed a system of inequalities before? Yes, that was the last lesson, remember? The shading and everything. So that's what we're going to be doing, and then picking a point in that feasible region. So that's our goal for today. All right, here is the one word problem that I'm doing with the exercise. So here's the scenario. If you have at least 24 coins in your pocket worth at most $1.70, and these coins are only nickels and dimes, then what's one possible combination of those coins you could have in your pockets? Like how many nickels and how many dimes? First off, anyone just have a guess off the top of their head? What do you think? You could just figure it out logically. You could just trial and error, right, and guess and figure it out. You got it? All right, so we're going to set up a system of inequalities to help us with this, all right, to help us figure this out. So here's these steps that I want us to do. The first thing we have to understand is what are our variables going to be? There's always going to be an x and a y, right? There's going to be two unknown quantities. Now in this scenario, I'm looking for what's one possible combination of those coins. Okay, so well, what are the two coins? They're nickels and they're dimes. Do I know how many nickels I have, or do I know exactly how many dimes I have in my pocket right now? No, they're unknown. So that's going to be our two variables. So we can say that x is the number of dimes, and y will represent number of nickels. Now it doesn't matter which one's x and which one's y, but you do have to set them up so that once we get our final answer, our x and y, we'll remember, hey, x, I got, I don't know, 10. What was that? Was that 10 dimes or 10 nickels? So that's step one, defining these variables. That just means telling me what is x going to represent in this word problem, what is y going to represent. All right, next thing, well, we're going to be writing these constraints, these inequalities. And to do that, we're going to look for certain keywords, such as I have at least 24 coins. All right, that tells me something pertaining to quantity, at least. At least means that that's the lowest number, that's the minimum. I could have more, but I need to have at least 24. And then the value of them, it's worth at most $1.70. So that's the maximum dollar amount that we can have. So those are keywords that we're looking for. If you see things like the word total or minimum or maximum, things like that, are all words you're going to look for to write these constraints. And now we need to actually write them. And so these constraints are going to have the two variables, x and y, in them. And they're going to pertain to the numbers that we've got in this word problem. So if I have at least 24 coins, now it doesn't tell me what types of coins those 24 are, right? Some of those 24 coins are nickels, some of them are dimes. I don't know exactly how much of each I have, but I know that if I add them up, so if I take the number of dimes and I add the number of nickels, right? Whatever those numbers are, I don't know what they are, that's why I'm using variables, but if I add those numbers together, it's got to be at least 24. Now, what we need to determine is what symbol goes here. So on the left side, I've got x and y, the numbers of dimes and nickels, and I'm comparing them to that 24. They need to be at least 24. What inequality symbol goes in there? What do you think? Less than or equal to? Greater than or equal to? So the word at least, it's a bit deceptive. Least makes you think lower, less than. But what it's saying is that the number of coins has to be at least 24, meaning that must be the lowest amount. 24 is going to be the smallest amount. So the numbers of dimes and nickels has to be more than the 24. So it's actually going to be a greater than or equal to. It's tricky. It's deceptive. But if you have at least 2 pencils in your pocket, could you have 5 pencils in your pocket? Right? You could have more than that too, but you couldn't have just one. All right, Michael, redemption time. The value is at most 170. So when I add up the total value of the 2 coins, or all the coins together, could it equal more than $1.70? Or could it equal less than $1.70? Less. Yes, because $1.70 is the maximum. So for the second inequality, that total value has to be less than $1.70, because at most that's what it's worth. It can equal less than that, but when I add up the value of the 2 coins, it can't be more than that. Now here's the next issue that students often have when writing these constraints. That first inequality, x plus y greater than or equal to 24. That was the numbers of nickels, the numbers of dimes, has to be or greater than or equal to 24 total coins, right? Because x is the number of one coin, y is the number of another coin, 24 is the total number of coins. The second inequality deals with the value, with the money. So am I going to just write x plus y again? Would that make sense if I add up the number of dimes I have and the number of nickels I have? Am I going to compare that to $1.70? Like if I have 2 dimes, do I say, oh, it's 2 dimes, less than 170? What do I need to actually look at with each of those types of coins? The value of each of them, right? So I can't just write x plus y. I have to talk about, well, how much is an x worth? What's the actual dollar amount right there? So the number of dimes is x. What's the value of 1 dime? Not all at once. I can't understand you when you all shout at the same time. So 10 cents is 1 dime, or 0.1. So the way to represent that value, because I don't know how many dimes I have, but I do know that if I add up all those dimes, I multiply them by 10 cents. So this is saying if I've got 3 dimes and I multiply 0.10 times 3, I'd get 30 cents. And that makes sense, right? If I have 3 dimes, I have 30 cents. You take 10 cents times each dime that you have. So that's the value from the dimes. I'm adding the value of the nickel. The nickel's 5 cents. What decimal do I use? Awesome. 0.05 Y. So the nickels are 5 cents. And so for each nickel I have, if I had 10 nickels, I'd plug in a 10 for Y, multiply that by 0.05, 5 cents. That tells me how much money I have in nickels. And so now this inequality, whoa, what it's really showing me is this quantity right here is the total amount of money I have from my dimes in my pocket. This term right here lets me know how much money I have in terms of nickels for my pocket. And then when I add these both together, that's going to be the total amount of money that I have in my pocket. And that total has to be less than or equal to $1.70, because $1.70 is the maximum number or amount of money that I have in my pocket with those 2 coins. Now there's one other thing we need to consider that's not stated in this word problem. So these two kind of tell us about how many coins I have to have. And with any of these quantities, there's another value that we need to also take into account. And that's at the bottom end, or the minimums. And this is just kind of a logic thing. If x is the number of dimes, I could have 1, 2, 5, 10, 20, 60. We're going to figure that out. What's the smallest number of dimes that I could actually have in my pocket? 1? Could I have less than 1 dime in my pocket? Could I have 0? Maybe. What if I had all nickels? Is that a possibility? If I had all nickels and no dimes? Could I have less than 0 dimes in my pocket? Can you have like a negative amount of coins in your pocket? No, you can't. So there is this bottom number, right? There's this minimum. We call that a ground or a floor. So there's these 0 constraints. Basically, X, number of dimes, has to be greater than or equal to 0. This is another inequality. It's another constraint. It's kind of like an obvious one where you think, oh, sure, of course I can't have, negative 2 dimes in my pocket. And then same thing with the number of nickels. It's got to be greater than or equal to 0. So there's just other 2 considerations we need to take into account. All right, now what do we do with these things? So we're going to graph these inequalities. We've got technically 4 of them. And we're going to graph these inequalities. It's a system of inequalities now. I've got 4 inequalities. That's a system. So we're going to graph them. And we're going to identify this feasible region, which we did last week on Thursday. And then we just find any point in that feasible region, and that's going to be various possible combinations of nickels and dimes in this scenario, okay? So to graph these, you could leave it like this, right? That standard form on the left. We know how to work that. But in general, if you want to rewrite these in slope-intercept form, it's going to make it a little bit easier. So I can change this to y is greater than or equal to 24 minus x. There's our slope-intercept. On the right, I'm going to subtract the x terms, 0.05 y less than or equal to 1.7 minus 0.1 x. Then divide by 0.05. Ooh, that's some tricky math right there. Y is less than or equal to, anyone know 1.7 divided by 0.05 off the top of their head? It's okay. We can cheat once in a while. 1.7 is 34 minus, okay, I know you guys know this one. What's 0.1 divided by 0.05? So like how many times does 0.05 go into 0.1? 2. Nice, Aiden. So then we got 2x. Now doesn't that look a little bit nicer to graph without those decimals? So it's going to graph these inequalities along with our 2 like 0 constraints. And then we're going to find this feasible region. And so I've got these 2 inequalities, and then also we've got our 0 constraints. 0, y greater than or equal to 0. Now, to graph these, 24 and 34, those are kind of big numbers. Usually we work with like single digits on the problems we did last week. And so one thing that we typically have to do is change the scale of our axis. Our axes typically represent 1, 2, 3, 4, 5, but we can represent them by any quantities, We can count by 2s or 5s or 10s or hundreds or thousands, depending on the values we're working with. And so if I need to get to 34 and I only have 10 lines here, what's a good number that I could scale my axes with? Any ideas? I'm going to make that a little bigger. All right, so If I count by 2s, I'd only get up to 20. If I count by 5s, I'd get up to 50 because I have 10 lines. So let's try doing that. So starting at 0, we're going to say, hey, this is 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. All right, that way we can reach the y-intercept for both of these. And then we'll want to scale the other axes the exact same way. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And then we can graph these lines, and we're looking for that feasible region, that shaded area. All right, that first inequality in green, 24 minus x. So 24 is my starting point. And if that line is 25, 24 would be just underneath it. And then the slope, that's a negative x. We treat that as like 1 over 1, down 1, right 1, down 1, right 1. So down 1, right 1. Now, also the nice thing is since both the x and the y axes are scaled the same way, or have the same values on each of those lines, if I go down 1, right 1, is that the same as going down 5, right 5? Why do you get the same slope that way? So since these are going by 5s, instead of going down like 1, right 1 and putting a teeny tiny dot, I'm going to go down 5, right 5 to make it easier. Down 5, right 5. Because it's going to be the same thing. It's like if I went down 1, right 1 5 times, that'd be the same as going down 5, right 5. So down 5, right 5. Down, right, down, right. And I don't need to go much further there because that's already like negative numbers. This is a greater than or equal to, so it's going to be a solid line. And then would I shade above this line or below this line?
Above.
Above it. Excellent. Thank you. It's a greater than symbol. And now with these systems of inequalities for linear programming, we're going to have a lot of lines. Whereas on last week's lesson, we had only 2 and the shading was easy. But now we're going to have, in this case, we've got 4 inequalities. If you start shading that much, it's going to get pretty confusing. So what I suggest doing is going to each line, and when you determine if you shade above it or below it, just draw little arrows on the line indicating like which way would be shaded. Then when you're done, you're going to have this shape with all these arrows pointing into one single feasible region, and that's the one you'll want to darken in, so you don't have to color in the entire coordinate plane. So here it's a greater than, so I know that, okay, that's shading above, above, above. So I'm just drawing like little mini arrows on it to show, hey, this is the side that would be shaded in. This is part of my feasible region, but you're just not going to shade them all in right at this second. All right, second inequality. Y is less than or equal to 34 minus 2x. So we start at 34 in this case. So here's 30, here would be 34, just underneath the 35 mark. And the slope is negative 2, make that into a fraction, over 1. And so I'm going to go down 2, right 1. And again, because my axes are scaled the same way, I can actually go like down 10, right 5, same thing as going down 2, right 1. So I'm just going to count the big lines. Down 2, right 1, put a dot. Down 2, right 1. Down 2, right 1. And then we can, it's a solid line because it's an or less than or equal to. We connect those dots. And here, do I shade above or below this line? Below, right? It's the less than symbol. And so I'm going to draw these little arrows below, below it. Ground constraints or the 0 constraints. And these ones are always going to be the x and y axes. So you don't really need to like do too much shading. It's basically just running one line along the y-axis and another line along the x-axis, which just pretty much says stay in quadrant 1, where x is positive and y is positive, because you can't have negative of something. And then again, you would shade, you know, above. I guess you don't really need to with these ones, as long as you realize you're staying in quadrant 1. All right, so we've graphed all 4 inequalities now. The final step is to shade our feasible region. And do you guys see one area that's got arrows pointing inwards from all the lines? If you see this little triangle right here. All right, see how that's got the arrows pointing inwards from every line? That would have the shading from all of my inequalities. So this right here is our feasible region. So basically, if we go back to that original word problem, which we've probably forgotten at this point, we're talking about how many nickels and how many dimes do I have in my pocket? What's one possible combination, given I've got to have 24 and it can't be worth more than $1.70. So if I zoom in on this little yellow triangle here, that's going to have all different possible combinations of nickels and dimes that I could have in my pocket. So we can just pick one. So if I go, I don't know, right here, this is 5. And so up to 5. So if I pick a point like right there, that's maybe, I don't know, 22, 23, something like that. So if that's a point in this feasible region, 5, 23, that's one possible point. Is that the only combination? Is that the only possible point in that feasible region? No. But it is a possible combination. You just have to pick any one of them. And then we have to think, okay, wait, what was dimes and which was nickels? So if we go back, x right here was the number of dimes. So I look at the x coordinate, which is 5. So we'd say I could have 5 dimes. And we can have 23 nickels. If I add those up, do I have at least 24 coins? Yep. And then if we multiply those out, 5 times 10 cents is 50 cents. And then 23 times 5 cents is 115 or $1.15. $1.15 plus 50 cents gives us $1.65. So that is less than $1.70, so it works. Yeah, you may. Anyone have a question about the math? I know it's very, very different. And we just need to practice. But those are the steps that we're going through today. That's not the entire process of linear programming, but it's the trickiest part. Trying to figure out how to write those inequalities and then graph them. So, any questions on how I got those inequalities or how we graph them or shaded or anything like that on any of these steps before we do some practice together? All right, well, like I said, the best way to get used to these is by practicing them. So that sheet that I just handed out to you, we're going to go through those. And for those of you at home, I mean, if you want to write this whole word problem down, you can. We've got 6 of them that we're going to work through together. And but otherwise, if you go to my P-Learning page on my calendar, then just click on the link for today, and then click on worksheet, and you'll get a copy of that pulled up. All right, of those word problems that I handed out today. Is focus on, so number 1, First thing we need to do on each of these problems is to define our variables. What does x equal? What does y equal? So define x and y. After we do that, then we need to write our constraints. Those are those inequalities. And then the last thing I'm going to want you to do for today is, instead of graphing them, because I know you're all pretty awesome at graphing already, slope-intercept formed is a pretty basic skill for all of you. I just want you to then, we'll call this like 2.5. Just rewrite each of your constraints in slope-intercept form, all right? And then we don't have to worry about the graph paper. We know what we're doing there. So rewrite in slope-intercept form. That's that y equals mx plus b. So those are the three things that I want you to do for each of these problems. So I'll do this first one with you, and then I'm going to give you some time to work through the other 5 on your own, and then we'll come back together and go over them all together to see how we did. So again, it's just something that you've got to practice to try to figure out, because it's not going to be the same way for every problem. So these are the 3 things we're doing. All right, here we go. I'm a baker. He's making bran muffins and corn muffins. Sounds delicious, right? And they're sold by the box. The baker can sell at most 20 boxes of bran muffins and 15 boxes of corn muffins each day. All right, at most. That's the most he can do for each of those types of muffins. It takes 1 hour to make a box of the bran muffins, and it takes 1 hour to make a box of corn muffins. And the baker only has 30 hours each week to bake muffins, regardless of the type. So that's our scenario. And before we start writing inequalities or these constraints, what are the 2 unknowns? What are the 2 quantities we're looking for? What's our x going to be and what's our y going to be? Any ideas? Muffins. So should I just say x equals muffins? Is that good? Is that a good defined variable? No. All right. So we're getting more specific here. What type of muffins? So what do you want x to be? The bran muffins? Yeah. All right, so there's one unknown. I don't know how many bran muffins to make. So x is the number of bran muffins. And then the other type are corn muffins. We'll call that y. Again, I don't know how many of each we're going to make, but these are our variables. So y is going to equal the number of corn muffins. And hey, that's step 1, everybody. When you do test on this stuff, which is not going to be next week, it'll be several weeks from now, the first part will be defining the variables. Do you all think you can do this? Define the 2 unknowns. Very good. Okay, step number 2. Writing constraints. Now, one of the trickiest parts about this is you don't know exactly how many constraints you have, right? Sometimes there might be 2, sometimes there might be 5. And so you don't really know exactly where to stop. So you have to look at each line, each sentence, and determine, hey, does that limit the number of this thing that I can have? And so just reading the next sentence, the baker can sell at most 20 boxes of bran muffins. Well, that's going to be a constraint, right? Because that's limiting the number of bran muffins that we can actually sell. All right, maybe he doesn't get many customers who like bran muffins. That's the most that he can get out of the store, something like that. So at most, 20 boxes of bran muffins. So I need to represent that with an inequality. And I see the word at most. So if he can sell at most 20 boxes, could he sell 25 of them? No, right? Because the biggest number is 20. Could he sell 18 of those boxes? Yeah, so he could sell less than 20, right? That works. But he couldn't sell more than 20. So we are going to use a less than or equal to symbol here. All right. Now, which variable do we use for bran muffins? X or Y? X. So our first constraint is going to be X is less than or equal to 20. Again, don't get tricked by that word most. A lot of times you read at most and you think, oh, most means greater than, bigger, more than, but that's not the case. It's saying 20 is the most. So 20 has to be the biggest number. X is going to be less than that 20. All right, after that, in that same sentence, 15 boxes of corn muffins. All right, that's also part of that at most statement. So what should this next inequality look like? First of all, are we going to use X or Y? Y, because this is talking about corn muffins. And then it's compared to 15. Will this be a less than or equal to 15 or a greater than or equal to 15? A less than, good. Because 15 is the most he can make. He can do 15, he could do 14, right? But he couldn't make 17 or 20 or 30. So Y has to be less than or equal to 15. Is that the only thing that limits us each day? No. So if you look at the next sentence, there's these time constraints, right? So not only is it an issue of like the boxes or the ingredients or whatever that we just wrote about, now we have to look at the time constraints. It takes 1 hour to make a box of bran muffins, 1 hour to make a box of corn muffins, and he only has a total of 30 hours per week to bake muffins. Now, instead of these being separate inequalities like that previous one, this is one combined one. So basically, like the baker, his oven, he can bake either bran muffins or corn muffins at a time, but not both. All right. And it takes 1 hour to make each of them, and he's got a total of 30 hours. So those 30 hours he can use however he sees fit. He can use some of the 30 hours for the bran muffins, some of those 30 hours for the corn muffins. We don't know exactly how many hours for each. But what we do know is when you add the hours together for both the bran muffins and the corn muffins, we're going to compare it to that 30 hours he has all together. So it's 1 hour for a box of bran muffins. So bran is X. So we can say that's 1 hour for every X, right? It takes 1 hour for every box of bran muffins. We rate that as 1X. So if he baked 3 boxes of bran muffins, you do 1 hour times 3, that'd take 3 hours, essentially is what we're doing here. I'm going to add the amount of time it takes to make a box of corn muffins. Well, that also happens to be 1 hour. So I'm going to write plus 1 hour per Y, 1 hour for every box of corn muffins. And when I add those two sets of hours together, I'm comparing it to his total of 30 hours. But which inequality sign do we use here? Can I spend more than 30 hours baking muffins? No. Can I spend less than 30 hours baking? Sure. So when I add those 2 hours to the left, that total has to be less than or equal to the maximum of 30 hours that the baker has per week. Are there any other constraints in this word problem? I think we got them all right. We looked through every sentence. We had some info from each one of those that we grabbed. Awesome. Then the last part I want you to do is to rewrite these in slope-intercept form. Now, when you have just a single variable, just the X or just the Y, remember those are just going to be like vertical or horizontal lines, so you don't need to rewrite those. But this last one, we'd want to change this into slope-intercept form. And that one's pretty easy because all you do is just subtract the X and then the Y is by itself. So I'm going to subtract that X. I'm going to write this as Y is less than or equal to 30 minus X. Also, I mean, if you want to keep the Y or the 1 in front of each of those, you can, but just dividing by 1 doesn't really change anything. So all less than or equal to 30 minus x. So I've just rewritten that inequality in slope-intercept form, so you could graph that. Start at 30, slope is -1 over 1, -1 over 1. And then last thing, remember we do have those ground constraints, but as long as you say in quadrant 1, you don't need to explicitly say that or explicitly graph it, but just know that, hey, I can't have negative boxes of bran muffins and I can't have negative boxes of corn muffins. You don't really need to write those out, but just keep that in your head that, yeah, obviously we're going to be staying in the positive numbers here. All right, so that's writing constraints. We got 5 additional problems on that worksheet for you. I'd like you to spend maybe 20 minutes or so looking through each one and trying to write these constraints. So do it just the way I did here. Read through the problem first and decide what your 2 unknowns are. What's going to be x, what's going to be y? What are the 2 unknown quantities that we're looking for? After you've got that planned out, then go ahead and try to write your constraints. What limits you in that word problem? So everyone at home, remember I've got this worksheet posted on my P-Learning calendar. I'll keep them up here for you also if you want. But if you go to my calendar and just click right here, 2.3a, writing constraints, you can get a copy of that worksheet. All right? All right, you know what? Instead of giving you just like a block of time to do all of them, I think it might be better if we work through them a little bit at a time together still to kind of guide you. Because some of you might still be clueless. I'd rather just kind of step you through it. And not sure what the situation is at home, but right here in this classroom, it seems to be a bit sleepy today. And I don't think that just giving you quiet time to work is going to be in anyone's best interest. So hopefully you've all had a few minutes to look at this one right here. And so let's try to think about this one together. All right, and then I'll give you some more time to do the next one, and we'll just kind of do one at a time, give you a little bit of chance to do it, and then we'll bring it back together, okay? Hopefully that'll keep us a bit more awake and alert. So we've got Fly With Us Airlines updating the security system at its airport, and the budget for new metal detectors is $75,000. So the word budget just means like that's all the money that they have for this purchase. The airline also has a maximum of 18 security guards that are available to work each shift that have to be operating the metal detectors. And there are 2 types of these metal detectors available. The Unit A metal detector costs $5,000 and it requires only 1 security guard. But the Unit B metal detector, that's the deluxe version, it costs $7,500 and it requires 2 security guards. And that B one, it's actually got a better reliability record. So it does a better job detecting the metal. And so then the person buying them says that you've got to buy at least 4 of those type B metal detectors. So first thing we've got to do is just define our variables. What are x and y going to equal? Any ideas? What are the 2 unknowns here? The what? Yeah, the units. What are the two different types of units that we have? Perfect. Yeah. So we'll say like X is unit A. So like this certain model of a metal detector, type A, whatever that metal detector is. And then Y will be the second type of metal detector, which is called unit B. Those are the two unknowns, right? I don't know how many of each metal detector we should buy. So now we need to write these constraints, these limitations for each of them. Now, the first thing I see when I'm reading through this problem is a sentence that says the budget is $75,000. Now, to me, that would represent some part of a constraint, right? Because can I spend more than $75,000 on these metal detectors? No, like that's it, right? That's all the money we have for these. Could I spend less than $75,000? Yeah, we could spend less than that. That'd be great. You know, my boss would be really happy or whatever. So we need to make an inequality dealing with money and compare it to the $75,000. And whatever the costs of the unit A's are plus the cost of the unit B's, when I add up those total costs together, it's got to stay under that budget. It's got to be under the $75,000. So do we know how much unit A costs? Yeah, what's the price of a unit A model? Right there. Unit A costs $5,000. So what we would do to write that is start by saying 5,000 for unit A. And if we look at our defined variables, unit A was an X. So for example, if we purchased 4 unit A's, I would take that $5,000 times 4, and that would be how much money we're spending on the unit A models, right? It's $5,000 for every one of those that we buy. So we represent that mathematically by writing 5,000x, $5,000 times however many we buy. I'm going to add that to the cost of the unit B models. Well, how much does unit B cost? Sure, $7,500. So unit B costs $7,500. So I'm going to add 7,500, but this is for the B unit, which we represented with a Y. So it costs $7,500 for every unit B. So I plug in a number for Y and I multiply it by that 7,500. That's how much money we're spending on this model. I'm going to add those two dollar amounts together. The amount of money we're spending on the A's, the amount of money we're spending on the B's, and we add those together, and whatever that total cost is, it has to be underneath our budget. So it's got to be less than or equal to $75,000. So that's one constraint, the money that we have available. So when I'm buying these two types of metal detectors for the airport, that total cost can't be more than $75,000. So it's got to be less than or equal. So that is one constraint, definitely, that determines how many of these we can buy. What else are we limited by? Like, why can't I buy 2 bajillion of these metal detectors? Security guards, right? We need people to work these metal detectors. So I can't buy like 50 of these metal detectors because we only have 18 security guards available. Now, some of those security guards are going to work the A unit, some of them are going to work the B unit. And so, however many A and B units we buy, we can't use more than 18 security guards. That's all we have. Could I use less than 18 security guards? Yes, we could. So this is going to be another less than or equal to scenario. Now we have to determine how many security guards are going to be used for each unit. So the Model A, Unit A metal detector, how many guards does that use? Just one of them, right? It says Unit A requires 1 security guard. So we can write that as saying 1 guard for every X, 1 guard for every unit A that we purchase, 1X. So if I buy 3 unit A's, that would take 3 security guards. 1 times 3 is 3. We're going to add the number of security guards for the unit B. Well, how many guards does unit B require? 2 of them, right? So unit B requires 2 security guards. So we'd write that by writing 2y, because it takes 2 guards for every unit B. 2 times y. So if we bought 3 unit Bs, we'd need 6 security guards, right? 2 times 3, 2 of them for each of those 3 units that we purchased. So this expression now, 1x plus 2y, represents all the security guards that we're going to be using for those 2 models. When I add them up, I'm comparing it to a total of 18. That's the total number of security guards I have available. Which inequality sign goes in here? A greater than or less than? Less than. Could it be equal to 18? Yeah, we have 18 available, so it could equal that also. This will be a less than or equal to 18. All right, so that was one constraint dealing with the money we have. One constraint dealing with the security guards we had available to work them. Are there anything else that's like determining the numbers of these units that we need to purchase? There's one last piece, right? What is that last little bit? We need at least 4 unit Bs. At least 4. So could we buy more than 4 of those? Yeah. Could I buy less than that? No. So which inequality sign do we use? A greater than. And that's unit B. So I'm going to use a y. So y has to be greater than or equal to 4. We've got to have at least 4 of these. So I can have more. I can have exactly 4. I can have more than 4. But I couldn't buy like only 3 of them because we've got to buy at least 4 unit Bs because they do a better job. All right, I think we've gone through every sentence. Is there anything else that we may have missed? Sure thing. You got it. So these are all the constraints from the word problems. We just want to write them in slope-intercept form. So just a little practice doing that. That first one in blue. So we can subtract 5,000x from both sides. So that leaves us with 700y is less than or equal to 75,000 minus 5,000x. And then divide everything by 7,500. If you'd like to grab out a calculator, by all means, you may do so. So then y is less than or equal to, this first one is easy. That's just going to be a 10 minus, and then 5,000 over 7,500 is going to give us a fraction. That'll simplify to 2/3 x. Doesn't that look a lot nicer to graph? 10 minus 2/3 x. Instead of 75,000. Can you imagine counting up 75,000 lines on like a coordinate plane to graph it? That'd be ridiculous. So that's our first inequality. The second one, dealing with the security guards, we're going to subtract 1x from both sides. That leaves us with 2y is less than or equal to 18 minus 1x. I'm not going to write the 1 because 1 times x is just x. Then the last step would be to divide everything by 2 to get the y by itself. Y is less than or equal to 9 minus 1/2 x. So there's our second constraint in slope-intercept form, ready for graphing. And then our last one, y is greater than or equal to 4. That's already in a slope-intercept form. If it's just a single letter by itself, we know that'd be a horizontal line where y is equal to 4, and you'd shade above it. So these would be our 3 constraints for this problem. Any questions on these? All right, why don't you go ahead then and try number 3. So read through the problem. I'll read through it with you. An electronics company makes 2 types of calculators, a scientific calculator and a graphing calculator. In a week, the manufacturer can produce no more than 450 calculators in all, and no more than 360 graphing calculators. So go ahead and take a few minutes right now, and I want you to first define your variables and go ahead and write those constraints. Take like 2 minutes, and let's see what you can do. All right, so number 4 says Chemo's material company hauls gravel to a construction site using a small truck and a large truck. The carrying capacity, so how much each type of truck can load or hold, is given in that chart below. And Chemo must deliver a minimum of 120 cubic yards each day to satisfy his contract with that builder. And the union contract with his drivers requires that the total number of loads each day be a minimum of 8. All right, so define your 2 variables, your x and your y, and then see if you can write those constraints. Take about a minute or 2, see what you can do. So right here in the middle of the word problem. Oh, first define our variables. What's x going to be, everybody? Yeah, small truck. Or how many small truckloads? What's y going to be? The large truckloads. And Chemo must deliver a minimum of 120 cubic yards. Now, it doesn't specify what types of trucks are going to be moving those 120 yards, but that's the minimum that he's got to deliver. And so we want to represent the amount of cubic yards from each of his 2 types of trucks. So how many cubic yards can a small truck carry? 12. So we'd write that as 12x, because that says we can carry 12 cubic yards for every small truckload. 12 times x. There's 2 small truckloads. That'd be 12 times 2, 24 cubic yards from those 2 small trucks. What are we going to add to that? What should that next term look like, do you think? 20y, perfect. Plus 20 cubic yards for every large truckload, 20y. And when I add those up, we're comparing it to this 120 cubic yards. And it says he has to deliver a minimum of 120 cubic yards. So which inequality do we use here? A greater than or a less than? What is it? Greater than. If 120 is the minimum, can I go over that? Can I do more than 120? For sure. Right? 120 is the minimum. So this has to be greater than. Could it equal 120? Is that okay also? Yeah, so it's going to be a greater than or equal to 120. So we've got to get rid of at least 120 cubic yards from that construction site. That's the minimum. I can go over that. I can do more. I can do 200 or 500. Now there's one other constraint here. It says that the total number of loads each day has to be a minimum of 8. All right, that's the total number of truckloads. Again, it doesn't specify whether that's small truckloads or big truckloads, but just there's going to be a minimum of 8. So what should that second constraint look like? Any ideas? Sounds good to me. So Ellie said x plus y. So those are the 2 types of truckloads, right? The small truckloads and the big truckloads. When you add up the total number of truckloads, it has to be a minimum of 8. So it's got to be at least 8. It can be more than 8 truckloads, but we have to do at least 8. So we're guaranteeing that those workers have at least some work that day, those drivers, at least 8 of them. are going to be hauling. All right, that looks like it's about it. Anything else? I think we got it. So then write these in slope-intercept form again, just to practice. So to subtract the x term from both sides, that leaves us with 20y is greater than or equal to 120 minus 12x. So I just move that 12x term over to the right side, then divide by whatever's in front of the y. So y is greater than or equal to, well, 120 divided by 20 is 6, minus 12 over 20, that's going to be a fraction, and 12 and 20 are both divisible by 4. So we can simplify that to 3/5 x. So this is what we would use to actually graph that constraint, to graph that inequality. The second one, nice and easy, just subtract the x. So y is greater than or equal to 8 minus x. And that's it. How are you feeling so far? Are you kind of seeing what to look for a little bit more on these now? Okay, we got 2 more to go through, and then that's it. Eliana, is your hand up? Okay. So here's the next one. The General Hospital, it's planning an aggressive advertising campaign to bolster the hospital's image on the community. Each television commercial for the hospital costs $9,000, while each newspaper ad costs $3,000. The advertising budget for the campaign is limited to $99,000. And also that advertising agency that the hospital is using, it's got the capability to produce a maximum of 23 ads or commercials during that time. So it can do 23 total ads or commercials, any combination of them. The TV ads, or the newspaper ads, or the television commercials during the campaign. So go ahead and determine those 2 variables, those 2 unknowns. And write your inequalities. All right, let's take a look at number 5 together. So our two unknowns are going to be the two types of advertisement. So it's either these television commercials or the newspaper ads, and we're trying to determine how many of each we should produce. So X can be the number of TV commercials, and Y could be the number of newspaper ads. Now remember, if you flip-flop those, if you made X the number of newspaper ads, that's fine, because your final step, like when you choose those points in the feasible region, like if you were to graph them, you would know that X is like the ad, the first coordinate is X versus Y. It won't make a difference as long as you put those correct units there. So each TV commercial costs $9,000, each newspaper ad costs $3,000, and the total budget they have is $99,000. So we got to stay under that $99,000 budget. So we just can say that, hey, it's $9,000 for every TV commercial. So we'd write that as 9,000x, right, for each TV commercial. I'm going to add the cost of each newspaper ad. Each newspaper ad costs $3,000. So we'd write that as 3,000y. $3,000 for every single newspaper ad, for every Y. And then when you add that total, add it all up, that's got to stay under the budget of $99,000. Anyone have that constraint written out? Yep. Okay, great. We're getting it. That's awesome. And then finally, the agency can only produce a total of 23 ads. That's the maximum, whether they're ads or commercials. So when I add up the number of TV commercials with the number of newspaper ads, that total has to stay under 23. So it's got to be a less than or equals to 23. I can't go over that. So that's going to be it. Anyone have that one also? Okay, wonderful. It's great to see. And then writing in slope-intercept form. Which we all should be able to do just fine. So 3,000 y is less than or equal to 99,000 minus 9,000 x. We divide by 3,000, and y is less than, is that 33? Minus 3x. I think that's right. Anyone else get that? Awesome. Then the last one, just subtract the x. All right. Now, we've got to practice this, right? That's how you get better at it. So far, I'm very impressed with everyone today in class. You've caught on to this pretty quickly. Let me show you your homework for tonight. All right, so on Delta Math, you've got these word problems. And so you're going to determine your variables, write your constraints, and then let me show you how this works, though, because this is going to be a little bit different interface. So everyone, please pay attention, and then you can pack up later. I promise I'll give you time to pack up. So first, you need to select the number of inequalities. Sometimes we have 2, sometimes we have 3, sometimes you might have 4. All right, notice that when you change the number, it just gives you more places to write it. Now, when you have your inequality, you first have to select which variable and then which inequality symbol, okay? So if it's a y is less than or equal to, you choose this one, okay? You write your expression here, 50 minus x, whatever it is. And then all you have to do is hit plot, and it draws the line on there for you, just like we had with the system of inequalities. And then after you plot it, you have to determine the shading. Now you click this switch shade button, because you have to determine, do I shade above that or below that line? All right, so this is a less than, so I'm going to shade below it. And then maybe your other one is x is greater than 20, something like that. So you plot that. There's the line x is greater than 20, and you can choose which side you need to shade. Okay, so greater than means to the right, for X. So these are all the numbers greater than that 20. So it's shaded in. And then if you have another one, you can graph it. Let's just say we just have these 2 for now. Now the final step that you would do, everybody, is choosing a point in that feasible region. All right, so you look at this double or triple shaded area and just pick any point like I did in that very first example. So I could pick like 30 and 5. So I could say, hey, there's got to be 30 tables and 5 chairs, if that's what your X and Y were. Maybe if your X were chairs, you would just switch these 2 numbers around. All right, so I've got you doing just 4 of these problems for tonight. Do you all think you can do that? Okay, I believe in you. You got this. I'll see you all on Wednesday morning. Bye, everyone.